Okay, can you guys see my screen?
Yes, Professor.
Yes.
Okay, that's wonderful. So let me actually let's get started because I think the time is exactly 5. First of all, thank you all for joining online. I got quite a few requests today because of flooding, because there's a strike on campus, and a lot of students wanted to see if we can have this lecture online. I said, why not? So, so I'll be teaching from my iPad today, and let's see what if I can see. So I'm gonna do slideshow from person view. Oops. So currently, okay, that's better. So first of all, we just as a matter of announcement, we're gonna have our first quiz on Wednesday. So make sure that you will be joining us. And also, well, if things change, I'll let you know. If, for example, that the picket lines is so much that it's hard to cross the picket line to go to the classroom, we might change the schedule, but otherwise we'll do as scheduled. The homework is due. You guys see the due date, so make sure you submit your homework ahead of the deadline. I think it's Wednesday, so that you can get a credit for what you do. I had 2 students joining my office hours to ask questions about the homeworks and so on. So if you guys in the future have issues with regard to lecture notes, to homeworks, and anything, you should come to my office hours. My office hours will be both in my office and also online. So by the time my office hour starts, I will log into Room so that if you want to ask a question remotely, you should be able to do that. But in a normal week, I'll be in my office as well. If I'm not in my office for office hours, I will send a notice ahead of time so that you don't come to find out that I'm not in office. So we'll do that. Any other questions before we start the lecture today?
Professor, we can't hear you.
problem. So something wrong with my iPad. What's going on here? Okay, cool. Can you guys hear me now? Can somebody say something?
Yes.
Yes.
Yes, we
Oh,
can.
Okay, great. Well, good. That's good. Sorry, something was going on. Somehow got me disconnected. At least with the sound, I was disconnected. Okay. So now let me go to my okay. Okay. So now you can see my screen, right?
Yes.
Okay, wonderful. So basically last week we talked about MOSFETs, and you all know what MOSFET means now. We talked mostly about saturation region because we'll be using MOSFET in the saturation region when we use them as amplifier. However, it's probably my mistake, but in homework there were problems that are using the MOSFET in their triode region. So when you do that, if you use the saturation region to calculate the current, you probably won't get it right because you have to go to the triode region. And just, I was talking to one student earlier that if we look at the MOSFET working condition, so I just want to write it here. So for MOSFET, so basically the one condition is that we have to have VGS larger than VT or VTN in order to have it. It can be either in saturation region, it can also be in triode region, but we wouldn't know whether it's in saturation or whether it's in triode region. So in order to do the second one is that we have to make sure is VDS is larger than what is it? VGS has to be okay. So let's draw the MOSFET for now. So this is VG. This is S. This is D. So basically VGD in this case. I don't know even how to erase my writing now. So VGD has to be larger than VGD has to be larger than VT in triode mode. But if VGD is less than VT, it's going to be in saturation region. So you're going to be using these two conditions when you calculate the MOSFET operating condition. If it's going to be, sometimes you don't know whether it's in triode or saturation. You can assume it is in saturation because the equation is easier, so that you can start to calculate the current and the voltage, and then afterwards you would verify which one is correct. So that's how you'll be doing that. So just some recap on what happens when sometimes you don't get the solution right because it may not be in the right region that you'll be working on. But today we're going to review BJTs. BJT stands for bipolar junction transistors. So basically you get a bipolar. So bipolar means you get two pole. Okay, so in this case, what you're looking at is a so-called NPN type of semiconductor. So in the middle, you have the P-type. P-type means it's a semiconductor but it got a lot of holes. And you get N-type on both sides. N-type means it's a semiconductor, but it's got doped with a lot of electrons, or a lot of free electrons. So then in this case, you have two p-n junctions. So you have p-n junction this way, you have a p-n junction this way. In the middle, we have the base. But when we connect this device with a voltage, and something would happen. The symbol for BJT for NPN is like this. For PNP, it's like this. So in this case, we're going to use a PNP. We're going to use NPN as example. So when we apply a voltage at the base, and then this is the emitter, this is going to be the collector. And then we apply voltage over here. This typically is going to be like a very small voltage. And what happens is that current is going to go into the base. And it's going to go through the base, and it goes through to the emitter. Because the current goes through the emitter, what happens is that in this case, the base current goes through the emitter, it causes the p-n junction to break down. So this voltage comes the current comes this way, this voltage across this one, and it causes this region to break down, and a lot of current is going to flow this way. So it forms a much larger current. So we call this IC, we call this IB, and we call this IE. In this example, the relation between IB and IC is that IC is equal to beta times IB. So apparently, because we at the bottom, so you can see IE is equal to IC plus IB, which is equal to 1 plus beta times IB. So that's the equation that we'll be using in what we call a linear region. Now, in the future, you will know that this BJT also has 3 regions. One is called cutoff, which means there's no current whatsoever. And the other one is called linear region. And the other one is called saturation region. I want to ask you to pay attention to the saturation region here, because in the BJT, the saturation region is very, very different from the saturation region in the MOSFET. The MOSFET saturation region is actually looked more linear. So I'm going to go to the next slide. So this is exactly what I drew in the previous slide. And if you look at the direction of like the big arrow, like this one, that indicates how the electrons flow. So the electrons will go from emitter, a little bit go to base. Most of the electrons are going to go this way. That's why you form a current from collector to emitter. And this is the symbol for NPN, and this is symbol for PNP. And this is where you have this circuit set up. And the relations, this is for the PNP, and this is the relation. So the first equation of IC is based on physics. That's IS is the saturation current, the VT is the thermal voltage. VT is typically about 25 millivolts, and VBE is here. So VBE is this voltage from gate. The other one, VEB is here. Sorry. So if you look at the NPN, if you know the VT is 25 millivolts and VB is given typically around 0.7 volts, and you know the saturation voltage, you can plot this IC. And once you connect IC, beta is a kind of amplification ratio, or the ratio between IC and IB, and you can calculate this. But if we plot this relation, it's very similar to This is we see. This is we see. VCE, and this is different IC. Sorry, this is IC. This is IC. This is IB1, IB2, IB3. For different IB, all you can say is VBE1, VBE2, and VBE3. So for different VBE or IB, you got different IC. And if you look at this carefully, this is very similar to the MOSFET, but only the names are different. So we're going to call this region is called a saturation region, and this is we call it linear region. And of course, this one here at the bottom is called a cutoff. The cutoff is the same, but remember in MOSFET, what we call them? In MOSFET, we call it ID, and this is VDS. And we call this region trial, and we call this region saturation region. And over here is a cutoff. So very similar, but different names. So this is something you have to be careful when we look at. So we're going to go through a few examples in this next couple, because you guys learned this in 330, and it's typically just give you a review. So I just want to go through some examples that also help you when you do your homework. Okay, so let's see. So in this example, we have NPN transistor. We have the base connected to ground. And then we have emitter connected to minus 15 volts. And we have the collector connected to plus 15 volts. And we know that this VBE is 0.7 volts. That's the given. And we want IC, in this case, we want 1 milliamps. And we want to design the circuit so that the current 2 milliamps flows through the collector and the voltage of 5 volts appear at the collector. So we want this, we see 5 volts. So for example, in this case, I think there's something wrong with this one. So maybe the problem IC 1 millivolts. I think maybe this is something wrong with this one. So let's do the 2 milliamps for now. So if it's 2 milliamps and width is 5 volts. So the first thing we can calculate is that we know that 15 volts minus VC divided by RC should equal to 2 milliamps. So in this case, we know that RC will be 15 volts minus VC is now 5 volts divided by 2 milliamps. So we get 10 over 5 milli, and then we get 2 kilo ohms. So we can calculate RC equal to 2 kilo ohms. Now also, we want to calculate VE, because VE is, we know that VB minus VE equal to VBE equal to 0.7 volts. So we know that VE is going to be VB minus 0.7, because VB is 0, so VB here is 0, because this is connected to ground. So VE is minus 0.7. So now we know that VE minus 15 divided by RE equal to IE, which is equal to, you remember, this is going to be equal to IC, so like beta plus 1 divided by beta times IC, which is almost the same as 2 milliamps, because it's only very small drop. So now RE can be calculated as, so V is 0.7 minus 0.7 plus 15 divided by 2 milliamps. This is going to be 14.3 divided by 2 milliamps. We got 7.15 kiloohms. So from here, we can calculate this RC and RE. So we get IC is 2 milliamps. Now, because if VC, now VC is minus VE equal to 5 minus 0.7 equal to 5.7 volts, which is larger than. Okay, so I want to ask you, do you understand what this means? If that VC or VCE is larger than 0.2, which means this transistor is going to be in that saturation region, is in that like the nonlinear region. Okay, so so somehow, you know, if we calculate the VC is larger than the saturation voltage, it's not in the saturation region. So, and then again, sometimes we do confuse between saturation and linear region, because this is not as in saturation, so this must be in linear region. If it's in saturation region, we see is 0.2. So that's what you would get. Okay, so here we calculated 0.2. Yeah, so I can. Oops, I just sorry. Something has happened. Let me go with. Let me erase this part. How do I do this? I'm sorry, but somehow I'm not able to use my erase. Something happened. It won't let me erase. Okay, let's I guess just move forward. I tried to learn how to use this. This one. Let me do it again. Should I erase it? Why don't you erase? Sorry. Okay. So when the IGBTs when the BJTs they can work in different regions, and you can calculate whether they're in linear region or saturation region. So in the BJT, what happens is, let me see, we have some student raising using, no, I'm not using OneNote. I'm using this. Yeah, I do use OneNote, but right now I'm using my PowerPoint annotation. So in BJT, sometimes what happens is that the actual relationship between the collector current and VBE is not totally linear, or it's not totally like a flat. Remember in the previous slide, I draw a couple of curves like this. But in real life, it's like this. So when if we extend this line, it goes on to this point. That point is called VA. And that VA eventually will help us determine how non-ideal this transistor would be. So this is something that we don't talk too much in this class. It's just some concept you need to understand. You might encounter this in your homework. But again, as we move on to this class, mostly we'll ignore VA is infinity. We just use that as a use a BJT in their linear region or active region, what we call. So if we draw the equivalent circuit for like a large signal model, basically we can draw this one here. So basically IB comes in and there's a voltage drop. Remember this 0.7 volts drop over here. And the collector has a current, which is equal to basically beta times IB. And so that's IC. And if the BJT is not ideal, you also have RO, which is the output resistance. And that's why we transfer this one to the next circuit. You see this. So this is equivalent to a BJT where you have IB coming in, you have VBE applied here, and you have this is E, and here you have IE, and over here you have IC coming in, and over here you have VC. So this is where the equivalent circuit is exactly this one. And the RO, you represent the internal, the output resistance when it's not ideal, which is related to VA. That's the BJT. Sometimes because the RO is, as I said before, we often do not consider them in our amplified circuit, so we simplify them. We simplify them in the different regions. We don't use this quite often in our class, but just so you know, there's different way to represent BJT in their DC circuit. Okay, so now let's look at another example. Let's see how if we can calculate the different voltages and currents in that circuit. So in this circuit, we assume that this beta is 100. So in this example, if we look at the voltages that are given, so basically VB is given at 4 volt, but VE and VC both are not given. So, however, if you draw, sometimes some students, actually at least one student asking me, what that arrow means, pointing to 10 volts, what that arrow means, pointing to 4 volt. Basically, if you want to complete the circuit drawing, use a voltage source. So in this case, this is what you have. So VB is given at 4 volt, but VC and VE are not given. However, if we assume this is in the active region, you can assume that VBE is going to be 0.7. So if VB is 0.7, because we know that VB minus VE equal to VBE equal to 0.7, we can easily calculate VE equal to VB minus VBE 4 minus 0.7 is 3.3 volts. So now you got VE 3.3. So the next one you'll be looking at here. So VE minus 0, which is ground, divided by RE equal to IE. So you can calculate IE. So VE is 3.3 and RE is also 3.3. So 3.3 divided by 3.3, which is K. So you get 1 milliamps. So now you find IE is 1 milliamps. You will be able to calculate IC because we know that 1 IC is equal to, well, basically IE equal to IC plus IB. We know this one. And we know IC is beta times IB plus IB. So now you know that this is equal to 1 plus beta times IB. So we can calculate IB equal to IE divided by beta, which IE is 1 milliamp divided by 100, you got 0.01 milliamps. Now we can calculate IC because IC equal to IE minus IB, because over here you know that IE equal to IC plus IB, right? So this IC comes in this way, IB comes in this way. You get nodal analysis, you get this IE. So this is how you get this equation. So it's 1 minus 0.01 get 0.99 milliamps. So now you have IC is given. So because if you look at this circuit right now, is time minus VC, this is VC here. Time minus VC divided by RC equal to IC. Now IC is given, RC is given, so you can easily calculate VC equal to 10 minus IC times RC, which is 10 minus RC is 4.7 times 0.99. You can calculate this to be 5.3 volts. So this is what we get. So I already have this circuit over here, which is give you step by step. Step 1, calculate we calculate this base voltage, and step 2, calculate the current in the base in the emitter, and step 3, you can calculate the current in the IC, and then also all calculate IB. 3 and 5 can be interchangeable, and step 4 you can calculate VC. So this is how you would calculate this circuit. Similarly, if you do this one, you can do the same thing. Basically, you can assume this is going to be 0.7 volts, and you can calculate this voltage over here, which is V is equal to 6 minus VE, which here we don't know. Sorry, 6 minus 0.7 gives you VE, which is 5.3 volts. And now you can calculate IE, 5.3 divided by 3.3. You can calculate the current. And then once you calculate current, you can get IC, which is just IE divided by 0.99. You can get almost IC, which is almost equivalent to IC. So now you can calculate this VC equal to 10 minus 4.7 times IC. You can calculate this voltage. Now, the reason we want to solve this is that if at this point, if VC is larger than VE, you know what it means that this circuit would work in the active region or the linear region. But if VC is less than VE, what happens? Which means it's not an active region. Now every calculation is wrong. We have to redo the whole calculation. So this is what I want to emphasize here. I believe that I already have also the circuit which is calculated already. Let me see if I can. Why is that this? Okay. Now I can erase this one. So you can calculate, you can see what I did. So, so which means here we have here, we got VC is 2.48, but VE is 5.3, which means in this case, your VC is less than VE, which means this is wrong. You cannot get this. So what it means that when we assume it's in the active region, that's wrong. It's not going to be in saturation region. It's not going to be active region. It's going to be in the saturation region. So in the saturation region, which means we're going to redo the calculation. So in saturation region, this voltage is going to be 0.2 volts. So that's a totally different calculation we have to do. So let's see. So here, if we assume this 0.2 volts, now the whole calculation is different. So the step one, we still do this. And we calculate the current over here. So which means if we calculate VE is equal to VB minus 0.7, we got 5.3 volts. And we calculate IE equal to VE minus 0 divided by RE. We got 1.6 milliamps. However, what the unique characteristic when the thing is not in saturation, not in active region, it's in saturation. When in the saturation region, IC is no longer beta times IB. So this one is given. So in this case, how would you calculate IC then? Even if you know IE, which means IB is no longer going to be, so IB is also not going to be IE over 1 plus beta. So these two equations are correctly given, which means even though I know IE, but I don't know, I cannot calculate IB because it's no longer, the equation is no longer right. However, we know that there can be 0.2 volts given at VCE. So luckily, from here, we can calculate VC because VC is going to be VCE plus VE. And VE is calculated at 1.3 and VC is 0.2. So we got 0.2 plus 5.3. So we got 5.5 volts. Now VC is given. So now we can calculate IC because we know IC is 10 volts minus VC divided by RC. And that 10 minus 5.5 divided by RC is 4.7. So we got 4.7. So we got 0.96 milliamps. So now we got everything correct. And so one more step we can do is, since IC is 0.96 and IB we can calculate it, because now let me do it here. So now IC is known and IE is known. So IB, because IE equal to IB plus IC, so IB is equal to IE minus IC, and IE is given at 1.6 minus IC is 0.96. Then we got 0.64 milliamps.
Hey, Professor, your mic's not working again.
I text him. Can you guys hear me?
Yeah.
I think he has a poor connection.
How about if I do this?
Yeah, we can hear you.
Okay, wow. This is tough. Something's totally turning my way. So this circuit, I just analyzed. Sorry that some of you could, many of you couldn't hear me, but the process of analyzing this circuit is to maybe what I'll do is I will simply just erase what I have, and so we can show this process. So what happened is when we calculated based on the active regions assumption, we found that it's not correct because this voltage here, VC is less than VE, which is totally wrong. So which means our assumption of it's in the active region is not correct. So therefore, we would have to redo this and assume it's in saturation. So when we assume it's in saturation, which is the bottom graph over here, is that in saturation, VCE is going to be 0.2. Now, because we know VB is 6 volts, so we can calculate VE equal to VB minus 0.7, which is going to be 5.3 volts. So therefore, we can calculate IE.
Professor, I believe your screen's frozen.
We can calculate IE is VE over RE, which is 5.3 over 3.3, 1.6 milliamps. Because we know VE and we know VCE, so we know VE here, and we know VCE, we could calculate VC is VCE plus VE equal to 5.3 plus 0.2, which is 5.5 volts. So now we know VC, we can calculate IC equal to time minus VC divided by RC, which is time minus 5.5 divided by 4.7. That gives us 0.96 milliamps. So in this case, we got IC, we got VC, IE, and we can calculate IB, which is IB minus IC, which is 1.6 minus 0.96. That gives you 0.64 milliamps. And then we can go calculate that beta modified is equal to IC over IB. That gives you almost 1.5.
Excuse me, Professor. Hello, your screen's frozen.
Oh, I'm sorry.
We can't follow where you left off.
So something is wrong. Let me, sorry, let me go. Look like this room still, oh, my room got disconnected again. I'm not sure what happened. 1 second. I'm gonna go to.
Recording in progress.
So in the last minute, I just redid the.
Professor, the sound is not working.
The sound is not working.
Now it's working.
Now it's working, but it's just echo. You guys hear?
Yes.
Can you hear now? Okay. So VBE has to be 0. So if VBE is 0, what it means? You cut off. So this is what this example will say. So if we want this circuit to be not in, so this is the analyzed result, okay? This is what I said. But if this circuit is, we want to make this circuit not in cutoff, we would have to increase. How would you do? So basically, we will need to change one of two things. One is that we can connect this one into with a voltage source. And this is one thing we can do. Another one that we can, so we can connect to VBB, and this is VCC. Other thing we can do is we can still connect this to ground, but we can connect this to minus VE. By doing both, we can get the BJT into either saturation region or in linear region. Of course, I mean, for the purpose of this class, we'll mostly get them into the linear or active region. There's another example where we calculated the different like node voltage, currents, and so on. So in this example, the top graph is the question, the bottom graph is the solved result. So I can do this step by step. Let me see if you guys still can hear me. Yeah, I see there's also, yeah, there's interruption with internet, it's probably due to the storm. So on the top graph, you can see that the top VBB is connected to 5 volts. However, there is, let me see, make this a little bit similar, probably. I mean, you can use blue. Okay, let me erase this one, it's too big. So the VBB is connected to 5 volts. And VE is connected to ground. And if we assume it's in active region, then what we can do is that we know that this VBE is going to be 3.7 volts, which is from here to here. So if we know VB is 0.7, we can calculate VB. VB is basically VBE minus 0, which is 0.7. Okay, so no. So now you got VB, so we can calculate IB. So IB will be VBB minus VB divided by RB. So VBB we know is 5 minus 0.7 divided by RB is 100. That's kilo ohm. So you got 4.3 divided by 100, so 0.0343 milliamps. So that's IB. So once we get IB, because we are showing the active, so we can calculate IC is beta times IB, and beta is 100 in this case. So it's going to be 4.3 milliamps. So now we can calculate VC equal to VCC minus RC times IC. VCC, let's see how much is VCC. VCC is 10 minus RC is 2 times 4.3, 8.6, which means VC is going to be 1.4 volt. Okay, so we got a VC 1.4, and we know that VB is 0, so it's larger than 0, which is VB, which means our assumption is correct. Assumption is correct. It is in the active region. So this is basically calculation is finished. But if in the process you find that VC is less than 0.2, just like for fun, if VC is less than 0.2, which means it's not in active region, which means we have to recalculate. We have to recalculate everything. So that's what happens when you have this assumption, and then later on you need to validate your assumption. And one more example, and we'll be done for today's lecture. Because again, I just want to go through these examples that will help you to recall what you learned for BJTs, and also help you to do the homework and help you to do the quizzes next week. So in this example, there are 2 ways to calculate this circuit. The voltage is given, and we assume it's in, we can assume it's in saturation to start with, because we don't know whether it's in saturation or not. because we have to calculate and then what verify. So to start with, we can assume if you see where I draw the IB, that IB is very small. We know that. And IB, if you know that IC, and we know that IB is IC divided by beta, which is typically 100 times smaller. So what I mean is that the current over there is so small, we can possibly ignore. So this will simplify that. We can ignore IB. We can assume IB 0. If we assume IB 0, do you see what would you get at VB over here? So VB now becomes a voltage divider. So what it means that you can calculate, because this total is 15 volts. The bottom is 50K, the top is 100K. Because the rate, the proportional rate, so you can easily calculate VB is 5 volts. Or if you still doubt, you can use 50K divided by 100K plus 50K and times 15 volts. So that will also give you 5 volts. So now you know VB is 5, so we can get VE. So VE will be VB minus 0.7, which will give you 4.3 volts. Because we assume it's in active region. Sorry, I actually made a mistake here. I made a mistake here. I need to correct it. Because I so much like try to, this is assuming oops. Oh, I cannot even bring that up. But what we assume is inactive. Active region, okay? Not saturation. So now we know VE, we can calculate IE. So IE will be VE over RE, which is 4.3 divided by 3 coulombs. It's going to be like 1.2. Divided by 3 is 1.4. No, 1.4. Yeah, well, almost 1.4, right? 1.43 milliamps. So we got IE because we neglected IB, so which is also equivalent to IC, almost IC. So now we can calculate VC. So VC is going to be VCC minus RC times IC, which is 15, minus RC is 5 times 1.43, which is almost 7. Yeah, so but this is a lot bigger than maybe 7 point some volts. So VC is much larger than VE. So this is larger than VE, which is 4.3 volts. Therefore, assumption is correct. Now, in this process, we neglected IB. So what happens if we do not neglect IB? We would have to do, there's one way we can do what we call Thevenin's equivalent circuit. We can do Thevenin's equivalent circuit, which means you can do, for this part, you can make it an equivalent circuit and then do the rest. Another way to do this is to do like a nodal analysis. Let me see. Is that we can do, so if we do nodal analysis on this circuit, I forgot to copy the finalized answer. Basically, you can assume this is IB, but there's current going this way. So if IB is not 0, you can no longer use voltage divider. So we will have to do really an equivalent circuit over here in order to calculate it. Basically, if you can write like this, the whole like super node over here. So the super node here, this VC, this VE, this VB. So we can write, for example, we call this I1, we call this I2. So we can write I1 is equal to 15 minus VB over 100K. And we can write I2 equal to VB divided by 50. So you can write I1, I2. Then we can write IC equal to 15 minus VC over 5. And IE equal to VE divided by RE is 3. 3K. Okay, this is 5K. So now we know that I1 minus I2 equal to IB. And we also know that this is IB. We also know that IC equal to beta times IB. We also know IE equal to 1 plus beta times IB. So now you see we have 1, 2, 3, 4, 5, 6, 7 equations. And how many variables we have? VB 1, VC 2, VE 3, 1, 2, 3, 4, 5, 6, 7. We have 7 variables and we have 7 equations. We can simplify. All these things to solve for VC, I1, I2, IB. It's not that difficult once you plug in all these numbers, even though it's 7 equations, because, for example, you can replace IE with IB, right? You can replace IC with IB, and then you can replace I1 and I2 with IB. So therefore, basically, you will simplify just having VB and VC 2 variables. So this is how you will calculate. So we're not going to go through the details here. There's one more example. We're going to finish the lecture. Is that this equation basically involves BJT in the N-type BJT or NPN and P-type or PNP BJT in the middle. What was given was assume beta is equal to infinity. So do you remember what means when beta is equal to infinity? Because we know that IC equal to beta times IB, or IB is equal to IC over beta, which means IB is 0. Because if beta is infinity, IC is fixed, so IB is 0. So in this circuit, what you can assume that this 0 amps, there's 0 amps here, 0 amps here. So that circuit is 0. So if you look at the given, what was given was the current is given, Q1 is 0.5. Oops. Oh. Okay, no, I got this one. Which is red line. So this one is this VCC is given at 5 and VE is given at -5. And we were given 0.5 amps milliamps over on IQ1, 0.5 milliamps on Q2, and 1 milliamp on Q3. Because IB is 0, so naturally you will know that this is 1.5 milliamps, and this is 0.5 milliamps, and this is going to be also 1 milliamps. Now, what was also given was 2, V3, V5, and V7. There is V7. So V7 is given at 1 volt. And V5 was given at, where's V5? V5 is given at minus 2 volt over here. And V3 was given at 0. So this is also 0 volts. Now, since many of the variables given, also in saturation, we also know that VBE is 0.7 volts. So right away, you can calculate V2, right? Because V2 is equal to 0 minus VBE, or VBE 1 equal to 0 minus V2, right? So V2 equal to 0 minus VBE 1. And VBE 1 is given at 0.7, so V2 is minus 0.7 volts. That's what you can get. So if you know V2, you can calculate R1. R1 will be V2 minus 5. Remember, there's minus 5 at the bottom here. So divided by 0.5 milliamps. So that's 0.7 minus 0.2. That gives you like 0.2 volts, which gives you 8.6 kilo. So you can calculate R1. Also, because V3 is given, so we can calculate R2. R2 will be really 5 volts VCC minus 0 volts divided by 0.5 milliamps. That gives you 10 kilo ohms. Similarly, you can also do the second transistor. So the second transistor, you can get a V4. So V4 will be 0 volts plus 0.7. So that gives 0.7 volts. So now you can calculate R3 will be 5 minus V4 divided by 0.5. That will give you also 8.6 kilo ohms, right? And then from there, you also know V5. So V5 is minus 2, so you can calculate R4 is minus 2. So minus 5, and then divide by 0.5, that gives you R4, that gives you 6 kilo ohms. And similarly, you can calculate R5, because R5 is given, R5 is 5 volts minus 1 volt, which is given. V7 is given, then divided by 1 milliamps. So that's 4 divided by 1 milliamps. That gives you something like how many kilo ohms will be going to be? With R5, it's going to be 4 kilo ohms, right? So, and then the last one will be calculate R6, because R6 is going to be this minus 2. Remember, this V6 is not given, but we can calculate V6 because V5 minus V6 is 0.7. So we can calculate V6 equal to V5 minus 0.7. That will give you minus 2.7 volts, right? So then R6 is going to be V6 minus 5 divided by 1 milliamp. And now you know that V6 minus 2.7 plus 5 over 1 milliamps. That gives you about 2.3 kilo ohms. Uh, 2.3, yeah. So it's going to be 2.3 kilo ohms. So that's how we finish the problem. And in the homework, I mean, in the book, it got other solutions saying, well, if you don't choose the exact R, because the R that we calculated is a numerical value, but actual R, you have to select according to the nominal R that is given in our R table. So the actual current is going to change. So that's how you can basically do the calculations. So now we're gonna stop the lecture slides. I will post the slides. I'll post the clean one so that you can work on it. I will also post the annotated one so that you will have both. So one will says noted, the other one says clean. So you have to both. There's one question from a student saying, how about the quiz on Wednesday? The quiz on Wednesday will only cover MOSFETs. So it's not going to cover BJT. So we're going to test the BJT on next Monday. Okay, so that'll answer your question. Not sure if everybody can hear, but I will post it here. We'll cover only
Thank you.
MOSFET. But if I want to open my OneNote, I wanted to do like just wanted to summarize maybe one thing here is that for the MOSFET and for the BJT, they are having a few little bit crazy definition in terms of their. So for MOSFET, we get a group of curves like this. And for BJT, we got a curve like this. And the regions, we call them, this is called trial, and this is called saturation. But for BJT, we call here saturation, we call this active, or sometimes we call it linear. And here we too, you can call it linear. So this is very important because sometimes I do the mistake too, but just make sure that when we write on paper, we understand what it means, active region. And of course, cutoff is always here. So the lines here corresponding to VGS1, VGS2, and here it corresponding to IB1, IB2, IB3, and VGS3. And the other thing that you want to summarize here is that when VGS has to be larger than VT in order to be in either triode or in saturation region. When VGS is less than VT, it's in cutoff. Here is when VBE is less than 0.7, it's in cutoff. When VBE is larger than 0.7, it's either in saturation or active. And this too is in saturation or active. Sorry, not active. In the triode. So in saturation region is what we use amplify. In triode region, we don't use it. Here is in the active region is we use a limit as an amplifier. In saturation region, the indication is that VCE is 0.2. And here, the indication is that VDS is larger than VT. Okay, so that's how we're gonna distinguish the different regions. Of course, you also got other differences like IC equal to beta times IB in the active region, but here you got ID equal to 1/2 K times WOL VGS minus VT squared. So here are the most important things that we'll be using in our next lecture. So I'm going to stop here and answer any question you might have. You can unmute yourself. You have a question, but I already answered like for Wednesday's for for Wednesday's quiz, work out MOSFETs only. And will be necessary formulas be provided. No, I'm not going to provide any formula, but it's open book, open notes. You can bring anything you want. Yeah, so you have access to everything. You can bring your book, your laptop. You can access anything you want. But the only thing you don't want to do is you cannot. I know some of you might have cracked like the homework solutions. You cannot use your homework solutions to copy. That's all you cannot do. So we'll test MOSFETs on Wednesday. We'll test the BJTs on Monday next week. Any other questions?
Professor, how long will the quiz be?
Give me 1 second. Look like I cannot hear very well. Let me go through my notes. Yeah, can you speak up?
Yes, I was asking how long will the quiz be? Like how many minutes will we have to solve it?
It's 50 minutes. 1-5. It's the last. It's typically start at 6, finish at 6:15.
Oh, okay. And
One or two questions.
okay, sounds good. Thank you, Professor.
Mhm.
Professor, how many questions on the quiz?
It's either 1 or 2.
Okay, thank you.
And why I say 1 or 2, it means it's like when you do the problems homework, you got one problem, you got multiple like questions. But in our exam, our quiz is only one of those questions. It's like a subset of one problem. Okay.
There's not multiple choice.
It is about no. Well, you ask a good question. The quiz is going to be posted like when I'm in the classroom, it will be posted on the blackboard or like on the screen. So it gives you multiple choices. But you have to do them on paper. You have to hand in your paper in order to get a credit. If you
Oh, okay.
yeah, I give you 2 choices. You can verify because the first one you can input it, you get it wrong, you can redo it, and before you hand your paperwork. So regardless what you submit online, you will not get a credit if you don't hand in your paper.
You have to show proof.
You have to show proof, right? But if you did it wrong, you hand your paper, you get a partial credit.
Okay. And it's open book, open note. Yes,
It's open book, open notes, right?
thank you.
And this lecture is recorded, so I'll post it as well. I'll post the link on YouTube. So if you needed to go back, you can go back. I know we lost the sound in some period of time. I'm sorry. Somehow this my iPad is not working properly in terms of accepting this microphone. I think maybe internet issue too. So hopefully it will be fixed in the future.
Okay, thank you, Professor.
Okay. Able to use our tablets for notes. Yes, you can use your tablet for notes, no problem. Look like if there's no more questions, ask it a little bit, but then I'll log off once most people are gone. But if you want to continue to stay for questions, you're welcome to stay for a few minutes. I'll be here. Okay, look like most people are gone, so I'm going to log off. I'll see you on Wednesday.
Thank you.